Okay, we're started. There we go. All right. Well, good afternoon, everybody. Hope everybody's doing well. It sounds like classes are going exciting in many fronts. Is that a final or an actual test?
Don't worry, the final only had, so it was assigned for Thursday, and we took a test last Tuesday. So we had 2 class periods, and then we were gonna have a test over.
That's awesome.
On Saturday.
Okay, so I will make a request. Right? We've got after today, we've got 2 more days. Okay? We do have a final. I don't remember when it is, but with my luck, it's usually one of the last few days before grades are due. I don't know how I always draw
the last day of finals.
Is it? Yeah, I'm either the last day or the second to last day. My entire time at Baylor, I've never gotten anything but that for any class I ever teach. I don't know how I draw this, but I'm like the lightning rod for bad final times. So before that, though, I usually like to have a review. There are no study days. My general opinion is the closer to the final itself, as long as it's not the day of the final, seems to have the biggest impact. Day of final seems to just be a sour grapes thing. Like nobody seems to really learn much from it. If it's the day before, it seems to have a pretty good impact because people can see what they got and they got a chance to change it. If it's several days before, you're going to have several other nasty finals in it and that. So what I would request is for next time, people bring whatever your schedules as far as you know them to be, so that we can try to pick a review time that will maximize the number of people who can be there and try to get it hopefully as close to our actual final time as possible. So that would be kind of my request on that, just so we can get that done well. There are finals that are up there with solutions. So again, my recommendation with those, take them as if they're timed. Right? Don't look at the answers before you try to solve them. Then use them to check yourselves. That will hopefully get you the maximum benefit from trying them. And don't do them just one right after another. Do one, try to figure it out, understand it, and then a few days later do the other. If you do that, that seems to do a pretty good job. If you take the quizzes after you have made your new study sheets, so I give you 4 sheets for the final. Theoretically, it's the 2 from the first half and then 2 new ones from the second half that's in there. It is cumulative, though I will put a heavier emphasis on the second half of the class. So that, you can kind of weigh it. I usually try to do about twice as much from the second half because I haven't been able to test it at all. So that's the basic kind of weighting scheme on those. But if you spend a little time to write out your second 2 sheets, review your first ones that are in there, and then take one of the practice, check it, find out where you're weakest, kind of fix that up, and then in a day or so try the other one, do it, and then we do our final practice time. Hopefully clear up any questions, you make any adjustments you need to your sheets, and that should hopefully get you in a great spot. I do encourage you with any other finals, that basic, how I'm trying to spread it out over several days you're studying, so instead of one intense thing. For the majority of people, particularly if you're handwriting your stuff, that seems to generate a lot better memory retention and a higher understanding. So there have been a lot of studies on that. So what you write with your hand seems to go more directly to your brain. And if you do it in small chunks over several days, it seems to last longer in your memory. And it's less prone to be affected by, fear and adrenaline. Right? And then just my best advice, once you've done as good as you can get a good night's sleep and come in and be relaxed no matter what. Right? Because if you get scared, adrenaline will block higher thought. Okay? So if you forget something, you start getting panicked, it will cause you to think less. the adrenaline will actually block your thinking ability. So if you've ever taken a test and you panicked and it was like horrible, and you walked outside the test and you're like, oh, it was that, that's what happened to you. Adrenaline kicked your rear, right? So there's nothing you could do to make up for the in-between stuff, but just try to breathe, keep calm, whatever you're in. You will then maximize what you can do because adrenaline won't hit you. Right? That's just some kind of general advice going into it. Because I hate to say it, but my own experience when I went through and with everybody afterwards is that they're going to stick like 3 finals all on the same day, right? And it's, when something happens there, your roommate's going to have a catastrophe, your computer will crash. I mean, just as many bad things as you can imagine will hit. So just get yourself as, kind of bulletproof as you can up to there, and it'll help you do better. All right, so that's my kind of quick overview to that. Today's going to be the last thing I'm going to technically test you on. There will be 2 more days that will be important for your future. Please listen. I am warning you it's not testable because I want you to relax on the last couple days. But I don't want you to skip it. They will be important for understanding a lot of stuff in the future. But my own experience is the last 2 days you're not going to be doing great design solutions on it. So what I'm going to try to put is all the connections to future classes that will help you to understand their ideas. We'll talk about how memory is designed. We'll talk about how these chips are designed if you deal with FPGAs in the future, so you go into any of the more advanced digital areas. We'll talk about some of the connections to memory for comp.org and a lot of these other areas. So we'll take what we've basically done here and show you how it undergirds future classes, basically. So that will be extremely important for you, but I'm not going to test you on it. Again, just because my experience has shown you may, if you stay relaxed, or remember it for a fairly decent while, but if I test you on it, you almost always get slaughtered. So I don't see a use to it. Right? But please do try to keep it in your mind because it really will help you in future classes. All right. So today we're going to do what I think is potentially on the math side of this, some of the most beautiful math you'll ever see. Okay? What this is going to be, it's beautiful because it actually has a really pretty picture. All right? It's elegant. And what we're going to be doing is how do we do error correcting codes? So we've done error detection before. That was the parity bits, the even and odd. We're now going to look, what if, and like in those cases, all I could do is tell you, it's wrong, right? I don't know what it is. It's wrong. You better ask for it again, right? Well, if I can find out that something's wrong, shouldn't I be able to, with a little more work, be able to figure out what was the right thing? Right? This was a question that bothered a guy by the name of Hamming. And so he spent a whole bunch of time and he actually came up with what's called a Hamming code, which was the first code that was out that's an actual error corrector. It will correct 1 bit. Since then, people have found it turns out you can make a whole family of these Hamming codes and you can correct a large number of bits. But the more bits you want to correct, the more check bits you have to include in to work off of it. It kind of becomes a self-defeating thing, right? You end up having to send so many bits that it would have been just better to just do it a few times and hope for the best. Right? There are other ones that kind of build off this too that use other ways of checking, what are called cyclical redundancy codes. Basically kind of like mathematics from encryption combined together. And those ones actually let you chain or fix a whole bunch of bits, but with different patterns. Like CRC codes, cyclical redundancy codes, will handle a whole bunch of bits, errors that happen all at once inside a larger thing. So most of it's correct, but there's a cluster of errors. And that might seem like an unlikely situation to happen, but it's actually a very likely situation to happen. So for instance, above our heads, we have fluorescent tubes. If you have your network cables running anywhere near those fluorescent fixtures and somebody turns the lights on, the fluorescent tubes create a really big electromagnetic field, and that will cause for the brief time that the lights are being turned on, you'll get a whole cluster of errors. And the rest of it won't. Right? Because that will interfere. If you put a satellite in orbit, right, there's going to be periods of times when the sun has high solar flare activity. And you'll get a lot of charged particles coming. And then most of it, the Earth's atmosphere shields you out and you're totally fine. So you'll get rushes of errors and that. Right? So I'm just mentioning these. There's a lot of other codes that are out there. I want you to realize to build on them. But what we're going to talk about today is that basic foundation type that will set up all the other ideas. Okay? So does this make sense so far? At least our goal, why we want to get there, and some of the things? All right. So let's remember for a sec here, what was the case with a parity bit? How were we able to detect the errors? All right? So imagine I just had, let's say, 2 bits that I want to send. Well, each one could be either a 0 or a 1. I'm going to call this one bit A and this one bit B. And then I'm going to add on to this an extra parity bit. Now, that gives me a total of 3 bits. I'm going to draw a Carnot map because we love Carnot maps. I've got 3 bits, so I'm going to draw a Carnot map appropriately sized. Now, I'm going to do slightly different than we usually do. I'm going to put P here just because I want to put parity bit by itself. And I'm going to put my A and my B. There. Okay. So let's say, for instance, I want to pick even parity. Now I've got several possible codes that I could send. AB could be anything. So I have 0, 0, 0, 1 is a possibility, 1, 0, and 1, 1. Those are my AB values. The parity has to make an even number of 1s. Right now I've got 0, so that's even. I've got only 1, so I have to add a 1 here, so it becomes 2. I've only got 1 on this line, so I have to add 1, so it becomes 2. I've already got 2, so I just put a 0, so it stays even. Fair? All right. So this one right here, right? Parity is 0. That's this top line. A and B are both 0. That's right here. This is my first code word. All right? 0, 0, 0. We agree? The second one, parity bit is 1. I'm on the bottom line. I want A is 0 and B is 1. Right? This is my second code word, right? A is 0, B is 1. And parity has to be 1. So that's this one. My third code word is right here. It's on, but I want A on, B off. That's right here. That's my third code word. My fourth one is parity is off, but both A and B are on. Parity is off, A and B is on. That's my fourth code word. So this is something neat that Carnot maps give you. It actually shows you why the parity bit works. And it works because no 2 codes are next to each other. So if you get a single bit flip, you're going to move to an adjacent square. But there's no other code there. And the reason why I can't correct anything is if I end up in this square, well, I could have come from the first code word, or the second code word, or the fourth code word. I have no idea which one it was. They're all equally likely. They're all right next to me. So that's why I can detect an error, but I can't correct an error because nobody's more likely. But this gives me an idea, right? What I need is I need to have a bigger spacing between my codes. If I have a bigger spacing between the codes, then I can transition to one of these other spots and not be next to another code. Does that make sense? So imagine in this case, what if I said, hey, look, I'm going to get rid of anybody who's even close by. Okay? So I'm going to keep my first code, but what if I say, hey, look, I don't want this code or this code or this code. What if I put a code right here? That makes sense? If I put a code right there, what I'd have is the first code word would be 000, and then this code word is P is 1, A is 1, and B is 1, 1, 1, 1. And if I look at the distance between them, I go, well, it's 1, 2, 3. It takes 3 bit flips, or 1, 2, 3. 3 bit flips, or 1, 2, 3, or 1, 2, 3. No matter how you want to count this, it takes 3 bit flips. So if a single bit flips, I'm going to end up in one of these spots, but I'm much closer to X than I am to first. So if 1 bit flip happens and I'm one of these ones adjacent to X, then I call myself X. And if I'm in any of the other spots, here, here, or here, I'm 1 next to first, so I can go to first. That is pictorially what Hamming's idea is. All right? And we call this distance how many bit flips? That's called the Hamming distance. That's the whole trick. And because it's 3, I can correct 1 bit. You have to make that Hamming distance bigger and bigger to correct more bits. 3 lets you correct a 1 bit. 5 lets you correct 2 bits. 7 lets you correct 3 bits. Gets bigger and bigger. That make sense? Okay. Now the question is, what would be a way that we can kind of build codes like this? And there's kind of an elegant way of looking at this. So this is kind of the what we want to achieve, why it works. Let's talk about how we're going to build an arbitrary size code. Now you can imagine right here, it takes 3 times as many bits as necessary. All right? I have to, in essence, repeat, I just send my code 3 times. If it's a 0, I send 3 zeros, a 1, I send 3 ones. But you can imagine that with this much extra space here, if I were to add 1 more bit, I double my size. All right? So I shouldn't have to add another 3 bits to get something useful out of it. Maybe I have to do a little more than double, but I need about 3 times. But that's about somewhere between adding 1 more bit and adding 2 more bits. So you would imagine that after this kind of initial cost, I ought to be able to add more bits a little cheaper. And that indeed is true. Right? Because again, you want about 3 times the amount of data, and I'm doubling every time I add a bit. So it should somewhere settle out between the 2 bits and 1 bit and 2 bit added, doubling and quadrupling. So far, so good? Okay. So let's think about a way we could kind of imagine this. And we'd ideally like to be able to know which bit is wrong. Okay? Now, if I were to just go to here, right, and get this code, which is both A and B is on and P is off, right? That's 0, 1, 1. I could see, since I'm copying them, that first bit has to be wrong. All right, that's the one that the error took place on. So I can fix it and move on. I want a systematic way as this grows to be able to do it. So ideally what I'd like is I'd like a check method that when I run through the check method, it returns the bit number where the error is. Does that make sense? Because that'd be really nice. If I had an equation and I could stick my data into the equation and it says location 5, I go to location 5 and flip the bit and I get a correct answer, that would be about as easy as you can get. It turns out you can do that. So that's what we're going to kind of develop. What we're going to want to say is in any string of bits, that's going to include both data bits and check bits. I want to be able to number each of these bits. Now, normally what do we number from? 0, right? 0 is always the correct thing to number from. But I can't do it in this case. And the reason I can't do it is there's a chance there's no error. So I have to have a no error code. And 0 is about as good of a no error code as you can get. So I have to leave 0 for no error. So I'm going to number my locations 1, 2, 3, 4, 5, 6, 8, 9, so on and so forth. Does that make sense? And the reason is I'm going to leave 0 equals no error. If you number from 0, you can only have errors, but that's clearly not going to always happen. You're not always going to have exactly one error. Okay. Now I'm going to take these numbers and I'm going to write them in binary. In this case, I've got to count up through 9, so that takes 4 bits. So I'm going to have 4 bits for this. So 0 is 0, 0, 0, 1. 2 is 0, 0, 1, 0. 3 is 0, 0, 1, 1. Now let me stop just here at the moment. And we'll notice something. Whatever I describe as a code has to still include this case. Okay? Now if you look on this, I've got these 3 bits here. And our statement is 2 of them are parity bits, they're copies, and 1's the original. So on here, I'm going to have 2 that are copies and 1 that's original. And I'd like the numbers to kind of somehow indicate that. Well, if you look at this, this has a single 1, this is a single 1, this has 2 1s. So it would be kind of nice if this was a check bit, this was a check bit, and this was a data bit. Right? That would fit nicely into this pattern. Check, check, data. Okay. Now, we know this, once I go past here, this is exactly 3 times, and we need that 3 times. Right? Once I go to 4, right, going to be different. But this won't be enough, so I'll need to add something else in here. And if you look at 4, 0, 1, 0, 0, that very nicely fits our pattern. I'd have to add another check bit at this point. And then my data bits would then go 0, 1, 0, 1. That'd be a data bit because there's 2. 0, 1, 1, 0. That's good, it's 2. Right? And I'd have my 0, 1, 1, 1. And again, it's still kind of fitting in that nice thing, keeping the number down, but it's growing a little, which we expected we would. We should get a little more efficiency, moving towards that 2 times. Right? So we've got here pretty good setup on it. Seems to make sense. Then at that upper limit, now we've got check bit, because it's just got a single 1, and then we start our data bits again with 2 and on. It turns out this pattern will exactly work. So every time there's only 1 bit in the number that's hot, it's a check bit. So I'm going to call this my square row and my triangle row. And maybe this will be diamonds. And I don't know, upside down triangle, is that okay? Just get different shapes. These are where my check bits are. Check bit, check bit, check bit, check bit. You'll notice they're all powers of 2. Okay. Where would the next check bit be? 16. Exactly. All right. So you can imagine it's going to get further and further apart as I start adding those bits. All right. And let's look at how we're going to calculate these. To calculate this check bit for this one, what we're going to do is everybody who has a 1 on that row is part of the square row. If it's got a 1 on the same row as square, it's part of square's calculation zone. It'll be used for it. The triangle, anywhere there's a triangle in triangles row, right, anywhere the 1 exists, it's going to be part of that first one's calculation. The diamond, obviously whenever there's a 1 on diamond's row, it's going to be part of diamond. And my upside down triangle, there we go. Fair? Okay. So let's see, how many bits did I give myself? 1, 2, 3, 4, 5. Let's see, we need 6, 7 to get an ASCII code. So let's imagine I want to send an ASCII code. I'll just add 2 more bits. 9, 10, 11. Obviously 10 is going to be 1, 0, 1, 0. So we'll have a diamond and an a triangle and an upside down triangle, and then a 1, 0, 1, 1. So we can add on to it as much as you like, no worries. But this gives me my data bits in between. So let's say I want to send my first initial, capital K. All right. Capital K, since everybody loves my first initial, they all memorize, that capital K is ASCII code 4 and then B. All right. Because in your spare time, there's nothing more fun than to memorize my initials in ASCII. Yes, I know that's not true. I don't even bother. In truth, I looked it up to verify I was right before I came down. All right. So in the data things, what I'm going to do is I'm going to put this in order. 1, 0, 0. I only put on the data parts. So all the D's here, I'm going to take them and I'm going to put this data in order. So 1, 0, 0, I go to the first data bit and I put the 1. The next data bit I put the 0. The next data bit I put the 0. And then 1, 0, 1, 1. 1, 0, 1, 1. There? I've now put the data in. I have to calculate the check bits. The check bits are going to be parity bits. And they're going to be even parity bits. So we're just going to do even parity bits of either the square group or the triangle group or the diamond group or the upside down triangle group. That make sense? So I can look here. Let's do the square group, for instance. So we'll calculate this one. I'll walk down all the other squares. I've got 1, still have 1, 2, still have 2, 3. I have 3, but I want even parity. So I have to go to 4. That make sense? There's a square, there's a 1. So that's 1, 1. I still have only 1, 1. The next square, 2 1s. Next square, still 2 1s. Final square, 3 1s. I need it to be even parity, so I need 4 1s. So I have to have 1 more at this. That's all you're doing. You're counting the number of 1s in all the bits that have the same shape. And you've got 1 bit free, so you can either not add or add to make it even. Does that make sense? Awesome. Somebody help me with triangles. Go for it.
It would be 0 because you have 1 triangle there, 0, and now we're at 2, and then 3, 4. So I would keep.
Exactly. See how it goes? Somebody help me with diamonds. Yeah.
Could be a 1 because there's only 1 with the
Yeah, see, we got the 3 diamonds right here. There's only a 1, so I need a 1. So now there's 2 in diamonds. And by having these ones only have one thing, they never overlap each other. All right, so basically they're free to change. That's the neatness about having them as a single one. Somebody give me upside down triangles. It is a 0. Why? Because you got 2. Hey, could not be nicer. This is now my Hamming code. I send this Hamming code. Now, you guys get to choose. Does an error happen? Does it not happen? An error happens. Where would you like the error to happen?
8.
Pick a number. 8? You like 8? Okay. So we're going to put an error on 8. So what actually gets received on the other end, I'm going to try to copy this real quick. All right. 1, 0, 1, 0, 0, 1. 8 gets flipped, so it becomes a 1. 0, 1, 1. So there is my copied number with a single bit error in location 8. Fair? Okay. Now, we're going to assemble together a verification. We've got 4 bits. Our least significant is our square, and then our triangle, and then our diamond, and our upside down triangle. Good? I just took them in the order that they appeared. All right, least significant bit to most significant bit. They're going to have the same exact locations. Right? So wherever the squares are, we're now going to exclusive OR, i.e. count up even, odd. All right? All the ones in those locations. So for the squares, I've got 1, 2, still 2, 3, still 3, 4. It's even. All right? Even on exclusive OR means it's a 0. Does that make sense? You just go through all of them, and you count up even or odd. If you end up with even, you write a 0. If it's a 1 or an odd, you write a 1. And that can be done by just one gate exclusive OR. In truth, generating these parity bits is just by done exclusive OR in the other ones. So exclusive OR completely describes this. So it takes one gate level, just 4 of them in parallel to generate this, and it takes one gate level, 4 of them in parallel to check it. So it's blindingly fast to calculate. Somebody help me with triangles. What should go here?
0.
Okay. All right? Because we've got 1 here, and we go to the next triangle, we get 2, and then 4. So indeed 0. How about diamonds? Somebody else.
0.
You're not somebody else, but that's awesome. All right. Part of the reason why I'm just going through other people, right? You'll get the best memory benefit by asserting something. All right? It's both scary, but it actually benefits. And I just, trust me, nobody's going to remember or care. All right? So don't worry about that. We're a safe place. Anybody jumps on anybody, I'll give you extra credit points. All right? We won't let that happen. So just take the opportunity to do it, right? So the diamonds are right in the middle. And we see in this one, right? For these, we end up with 1, 0, 0, 1. So indeed a 0. How about the last one? Somebody who hasn't gone yet. It's a 1, right? Because it's the last 4 bits, and there's 3 of them. So that's odd, so it's a 1. So the location where your error was 8. 1, 0, 0, 0. That's the number 8. It tells you where the location was.
Wait, I'm super confused. How did you do that again? Like
Magic.
square, for instance?
Okay, so the way the square works is you go to wherever the square things are, right? It's in the first one and the third one and the fifth one, right? All the odd ones,
Okay.
right? Now, watch. Before this lets you blow it, since I'll do it here, we'll go through and I'll show you why it does what it does. Right? So the first one is telling you, is there an error in the odds? If the parity bit is right, there was no error in the odds. If the parity bit is wrong, the error was in the odds. So the first one, when you look at it, I've got 1, 2, 3, 4 ones. It's even, so that's a 0. No error in the odds. And indeed, the error happened in 8. All right? So no worries there. All right? It just told me it wasn't any of the odds. Now, you go to all the ones that have the triangles here. This happens to everything that has a 2 that's used to add in to get it. Right? This was involved a 1 added to it. So like 6 is 4 plus 2, so on and so forth, right? So all those ones in groups. So you see 2 and 3 are here, right? And we've got 6 and 7, right? And then 10 and 11. And so in the triangle, it checks to see any of those have an error, right? And if you count them up, you'll find out that there's an even number of them, right? If you walk through, right? So the triangle's 0, 1, so I've got 1. All right, 2, 3, 4. It's 4, it's even, so there's no error in that. So that means 2 and 3 and 6 and 7 and 10 and 11 don't have it. So now you're down to just these 2 locations. Okay. And this one right here checks the lower half, and this one checks the upper half. It's possible there's no error, in which case you get all zeros. Since the error was here, it's going to generate an odd number here, which triggers 8. It's not quite as mystic now. All right? But you can see it's actually a very clever use by picking the bits, right, which are the pure 2 to the n's. It allows me to do an overlapping set of things that will uniquely identify where the error goes. And this was the observation that Hamming made. And that's what actually made those, like, you know, big cool moment here. That make sense? All right. So let's do another example of these. All right. We'll pick some other thing we want to transmit other than an ASCII code, or we can do an ASCII again if you want. All right. And if we finish it, this is the other big thing that I need to understand, basically how these work, right? And we're doing both sides. How do you encode it, and how do you decode it? All right? And once you've decoded, I would fix this bit, and then I just extract the data bits as my data, and I ignore the check bits, and off I go. All right? Yeah.
I'm just trying to think about this in my head. How would the process be for, it would obviously be more parity bits, but to find 2 errors at once? Or is that possible?
So you can, but it does become more complicated to be able to find them, right? So you have to now go up to, instead of the Hamming distance of 3 between them, you have to go to a Hamming distance of 5.
Okay.
Right? So it becomes a more complicated. It doesn't have a pretty little scheme like this. Right? You have to go to a more complicated one. So instead of the 3 being your start, 5 is. And then you have to do it at 5, 9, so on.
Okay.
So you would need 4 parity bits checking and then a data bit. And before you add it. So it gets ugly really quick. Right? Oh. So that's why I stick with this one. And in truth to you, correcting 2 bits on there, if you're getting 2 bits in a small area of data, you're probably better off trying to fix your data line. Because think about it, for most of these cases, like a typical case, like if I've got RAM or something, the likelihood to get a data bit flipped in RAM is usually rated somewhere around 10 to the minus 11th. Right? That's a really infrequent number. However, you have a really high clock rate and you have an awful lot of RAM. So that actually generates errors in a reasonable data range that you have to change them, but it's really, really sparse. Right? I don't want to go for two happening. What turns out is usually if an error happens in one spot, it actually is more likely that another one happens nearby. And the typical reason is, why do these errors happen? Right? And one of the reasons is like a charged particle comes in, like an X-ray or something like that. If it's a data line, right, like I said, it could be coming too close to some really powerful machine that turns on, creates a big electromagnetic field. On old monitors, you know, it was actually possible when you turned all these big, they used to, instead of being flat screen LCDs and all the rest of this, we used to have these big electromagnetic tubes, right? And when you turned them on, there was an electromagnetic field that went for quite a bit. And so those ones, if your cables were too close to those old style tube monitors, you could easily get data bits flipping from that. Things of that sort. So they tend to be close. Somebody brings a magnet too close. Right? You know, like I said, radiation is another common one. A surge coming down the line. Memory closer to the power area is more likely to get affected. If there's an internal failure, a short will go out from there. Data right around where the short occurs is more likely to get flipped than one's far away from it. So they tend to cluster. So the real thing is when you have to get to multiple, and we can do it, but it's often more efficient to take into account the spatial locality of where the problem happens, and that's where these things called cyclical redundancy codes come in. And basically what a cyclical redundancy code is, you get a polynomial where the roots are somewhat close together and then big space around them, and you pick that root pattern to be something that describes the spatial resolution that you want to get down to. And then we actually calculate, instead of doing, you know, these exclusive ORs parity bits, we calculate all the roots for your shifted data bits, and that's actually what comes down. All right, and those codes, it turns out, they'll give you high resolution in any shifted polynomial form. So basically you'll get that kind of overlapping pattern of the roots, which lets us get kind of high resolution in certain areas. That's kind of the idea of it. But like I said, that's more than I want to do here. If you have to do it, like take a networking class, and they'll go into detail on CRC codes and that. But for our purpose, this is good enough. Would you feel comfy first cut? Okay. How big of a data do we want to do? We want to do another ASCII? We want to do a BCD code? What makes you happy that we want to send? BCD is fine? Awesome. So BCD has 4. So I'm going to need a check bit and a check bit. And we'll have our first data bit. And then a check bit and a data bit, data bit, data bit. That's how it's going to be set up. Because the first spot is 1, 0, 0, 1. We're going to need 3 bits here. Next one, 0, 1, 0. 0, 1, 1. And that's 2. Next check bit is 1, 0, 0. And then 1, 0, 1. That'll be a data bit. 1, 1, 0. Data bit. 1, 1, 1. All right, what BCD do we want to send? Pick a number 0 to 9. 7? So 7 is 0, 1, 1, 1. Huh? Now, you could get used to it just looking on the lines. I often find it helpful to just kind of do the squares and whatnot. So all the address bits that have a 1 in it on the lowest one. We group, and let's see, we did this as triangles, so we'll do all the ones on the 2 line. And I think we did diamonds next. Good? Okay. So since you are all now experts at this, help me out. Somebody help me with the square check bit.
0.
Okay? Because we've got 0, 1, 1, it's 2. So it's already even. How about the triangle? Someone else.
0.
It is 0, again, because 0, 1, 1. So 2, again, even. How about diamonds? It is indeed 1, right? Again, because last 3 bits, and there was 3 of them, so we need the 4th.
Yes.
Yay! So this is our code. That is what you would send, or that is what you would store. All right? So if I want to do this, I could actually make 7 bits of memory to store 4 bits, but then even if an error happened after I'd stored it, I could fix it. This is the basis of what's called ECC memory, error correcting code memory. This is the simplest. All right. So now we want to transmit. Do we want an error?
Sure.
Okay, where do you want the error?
2.
Number 2? Everybody like 2 as an error? Awesome. So it comes down to the other side. And we get 0, 1, 0, 1, 1, 1, 1. All right. We can use the same addressing pattern up above. I only need 3 bits now, though. And we'll put square, triangle, diamond. Again, diamond is on the left because that's my most significant bit. That way I can read it like a number. Okay, and just to show that it doesn't matter what the order is, can somebody calculate for me diamond? We'll go in reverse.
0.
It is 0, right? Because you look at all 4 of the diamond bits, and they're all 1s, so there's 4 of them. So that means it was even. Right? Triangle.
1.
It's 1, right? Because I've got 1 here and then another 2. So I've got 3. That's odd. And then square,
0.
it is indeed 0, right? 0, still 0, 1, 2. So 2 is even, so we write a 0. Which means your error is in location 0, 1, 0, location 2. There's your error. It got in it. That's cool. So this is your transmitter, that's your receiver. Let's quickly draw what the circuit is. Now if we have some time, I can kind of punk the future here a little bit. All right. So if we consider the first one that's here, for this, imagine I want to just transmit a whole bunch of these, so I might build a custom circuit for this. Well, what I would have to do is wherever these, the square ones are, that aren't the final check bit, that's the source for the encoding one, and the destination is the other side. So I could take this one, and this one, and this one, and they all have to go into an exclusive OR. And it outputs right there. All right, so I could load into the data bits, and then I take one more cycle, and it would calculate this, and I'd load the check bits, and I'd transmit. So the triangles, again, same thing. All right, this is my destination. The remaining ones are the sources. All right, so I've got this one, and I've got this one, and I've got the one next to it too, I believe. Yes. These have to go into an exclusive OR, and it calculates to that position. All right. Basically, I took the 3 triangle sources. That was my starts, and my destination was the final one. Somebody help me drawing the last one?
It's just the last 3.
Yep. So we go to the diamond, and that's the last 3 of the sources. I'm going to do it up above so I don't get a really ugly looking thing. And then what?
Goes into the last check bit.
Yep, I put it into the exclusive OR check bit, and then stick it down. That's it. That is the circuit to build this. All right. You load the data, hold it for 1 cycle. Next cycle, the check bits show up, transmit. You can do it even quicker if you want, if you load it in on the half cycle, right? Load it in the first half of the cycle and update the check bits on the second half. You can do this really quick. But that's a pretty elegant little circuit. How about on the other end? What would the circuit look like on the other side? Well, now I'm trying to calculate these 3 little bits to tell me the address, right? So now every square bit is a source, and the square bit on the end here is the destination. So I can just run through every other one here. And we use the same completely awesome exclusive OR. And you output it to there. That's all that's required. All right, the triangle grabs these 2 and the second one here too, and it grabs these last 2. All those 4. And it runs into there. And then the final one, the diamond, takes all 4 of the last bits. Runs it into an exclusive OR. Oops. Fills in the last bit. Yeah.
So you'd be throwing all, like each member of each group into the same XOR. You don't have to have multiple XORs just in parallel.
No, you could do it all into one.
Okay.
And remember, so I could, with 4, I could either take a 4 input, or I could note that that same XOR is the same as doing 2 separate 2-bit XORs and XOR in the result.
Okay.
So if you didn't have a 4-bit XOR, you could generate it from 2.
When you have an XOR that has more than 2 inputs, it just spits out its odd or even.
Odd or even.
Okay.
Yeah. That's a nice thing. That's why XOR is actually the gate for this. Because it is an odd or even check, and that's all we do with parity checks. That's why we actually picked parity checks. Because it splits everything in half into groups nicely, and it does a really good job with that whole odd even distinguishment. Yeah.
So the first circuit is the transmitter, and the second circuit is the receiver.
Yep. This is technically to calculate to transmit, and then somebody would transmit it down the line. And this is to check it after, but this is the receiver's check. If that's all zeros, you're good. If it's anything other than 0, you flip that bit. And you could set up a pretty nice state machine to do that. Good? Awesome. Well, we've walked through everything. You've gotten some examples. I do have some more examples online. I am happy to do more, but I don't also want to be a dead horse. I think it's elegant enough that it's easy to get. So I'll give you the option. We got about 15 minutes. I can either start next stuff, or we can review some of the old stuff.
Review.
Yep.
Okay. So what stuff would you like to review? There's a lot of things to go over, and I don't want to pick something that's not important to you. So is there
a way that you could somehow summarize, like, quickly go over everything that we've learned since the last test, like just like a big overview kind of thing?
very high level?
Yeah.
15 minutes. You can do it.
Well, I can't. I don't know how much use it is to you. So let me break it down this way.
Gotcha.
Right? I'll break down what the big ideas of each chapter were, right? So that you know what happened in each chapter, and then you can tell me whether or not we should go into that in any more detail.
Perfect.
Okay, so chapter 5. The big idea of chapter 5 was how do we even build memory in the first place? So we started with latches, with or without an enable, and we worked our way up to flip-flops. We started with SRs, which were dangerous. We eventually built Ds, and then Ts, and then JKs. So we got fancier and fancier ones. So what we ended up with at the end, because this is what we cared about, was a flip-flop, 3 different varieties that were edge-triggered. Right? That's what flip-flops do, edge-triggered flip-flops. We had the D types, we had the T types, and we had the JKs. We said all of those are basically safe to build with. We went, yay, okay, now we've got our design builds. Then we have 2 things we want to do with these. One of them was analysis. You're given a circuit, what the heck does this do? Right? So we start that by, you do analysis the same way you do anything else. You take a look at what's needed on inputs, and in this case that'll be inputs plus what is the current state, which we use little q for current state. All right? So we took the inputs and the little things, and we walked through every possibility. All right? And we took a look at what was going to be the next Q. And we did that in the following process. All right? We first took all those inputs and current states, and we calculated what was the output of the combinational circuit portion. Because remember, it goes into a combinational circuit first to calculate the next state. And then that goes into the flip-flop. So we calculated the inputs to the flip-flops, the combinational circuit, and then we used the characteristic table of the flip-flop type we had to figure out what the next state was. And then we knew what the next state was, so now we knew how the states transition, which told us basically how does this circuit work. And that's what we meant by analysis. You were given a circuit, and you could figure out, you know, what is the state table for this. You could draw a figure of it if you needed to, all kinds of fun stuff. Does that part make sense? All right, the other thing we had to do with these was somebody told me, hey, I want you to build this, and then you had to figure out how to build it. And we called that the design part. And what we took was a whole bunch, again, we picked our flip-flop type that we wanted, and they told us for these inputs, we want the following state transitions to happen. Okay? So then we said, okay, now we know what the inputs are. We need to figure out what the outputs of our combinational circuit is. We don't know that. We know the inputs to the combinational circuit, and we know the outputs from the flip-flops. But we also know what the flip-flop is supposed to do. That's what they have to tell me, right? They want this to happen. I have to figure out a combinational circuit that'll do it. Well, then we took our excitation table, because the excitation table said, what did you want the transition to happen? What should little q go to big Q? And looking at that, it said, what should the input be to the flip-flop? So they told me what transitions they wanted and what inputs they wanted to cause those. And then we could then take that and say, okay, take the excitation table and figure out what the inputs should be to it. And now we know the inputs to the combinational circuit and the outputs of the combinational circuit. That's the inputs to the flip-flop. Right? And by knowing the inputs and the outputs, you can put it in a Carnot map and you're done. Right? That's essentially first half of the course. That was all of chapter 5. Right? We spent probably 2.5, 3 weeks on that, but that's really all it was. Eventually building up to flip-flops, 3 types, and we either had to analyze things or we had to design things to accomplish stuff. That type of designs were typically done for small scale stuff. Okay? Then we go to chapter 6. Chapter 6 introduced 2 big categories. One is registers, and the other is counters. These are kind of bigger scale structures that are very commonly used. So one of the things we want to get from something really small like we were doing before, we want to get bigger, so we need bigger memory. So we introduced 2 different types of memory. We had parallel, and then we had serial. That was the kind of 2 general categories that were out there. The parallel ones is what you have in your typical computer. A parallel memory just has a whole bunch of D-flops, flip-flops in parallel, and they all have the same clock. Right? So they're going to run through those. Serial was you have one D-flop fitting into the next one. So they're just kind of patched one after another. Okay? The whole trick of those 2, right? The parallel ones, you can access all bits all at once. Right? But it takes a lot of wires in and out. Okay? So that basically is going to be done for a situation you want very high performance. You want very fast. You don't care how much space it takes. The serial one can hold every bit as much data, but you can only access them 1 bit at a time. So they were much smaller. You had less wires. You had 1 bit coming in, 1 bit coming out, but they were slow. Right? So parallel is kind of like your high performance thing. That's your sports car. Right? Serial is like your subcompact, right? It's small and efficient. So you got to decide which one you want. And then we had a couple that were hybrids. That's what we called universal. And basically those ones were ones that often had like a parallel in and a serial out, or a serial in or a parallel out, or both. And it allowed you to switch between them. And we often do that because imagine for a sec, I had a data bus between 2 computers. Well, I have a single wire to send data down. So I would need a serial register to be able to pass them in 1 bit at a time down the wire. And somebody on the other end had to send serial bits. Right? Maybe even with a Hamming code. Right? So I would have those to do the transmission part. But the internal part of the computer is going to all be in parallel. It's got wires coming in and out to my flip-flops. So what I want is something where I can take the parallel bits and I can load them 1 at a time into their respective areas, and then I can send them out. Right? That's a parallel in and a serial out. Right? On the other side, I'd have a serial coming in, and then I'd have a parallel that has to come out that goes into my next internal memory bit. Make sense? So like when I'm dealing with a bus connecting or a network connecting 2 things, these universal flip-flops are often used, right? Universal registers. Right? Parallel in, serial out, or vice versa. That make sense? Okay. So that's basically what we did with registers. The second half was counters. We had a lot of different counters. So we split them into different types. The first one was we had ripple counters. Remember the ripple counters were the ones where each bit kind of changed at its own little pace. It's kind of like the old style clickers going into a stadium when they count people, or the old style odometers on the dash of a car where it was those little wheels that would trigger around. And what happens is 1 bit, when it rolls over, it pushes the next bit. But since the low bit has to roll to push the next bit, they don't happen at exactly the same time. It ripples. Okay? We said that it's really easy to build, and we built those really quite small and efficient for both binary and for BCD. But they really stink if you're going to implement them on an FPGA. So much so that you really can't practically build them. Okay? Because FPGAs want one clock. They don't want you to use, a data signal to become a clock for somebody else. And we had to, ripples use data to act like a clock. So those ones were no good for our FPGAs. So synchronous was the right way to do for the FPGAs. And so we built synchronous versions of those same things for both BCD and binary. Okay? And binary says you're kind of generic 2 to the n. Counters are super common, right? You've used them all the time up in your lab. You've used them to, how to slow things down so you could output to the 7-segment displays, right? To time them when you're flashing lights on and off and all kinds of other stuff. They're just used all over the place. If we have to go from one clock speed to another, we use a counter to downsample. So counters are very, very common. So we had those. And then we said, that's great. Those are some very typical counters. We added 2 more non-binary counters and then a special case of the binaries. Right? So the 2 special cases were ring counters, which basically let us count in 1 hot style. Remember, 1 hot, only 1 bit is on at a time. And so the ring counters allowed us to count 1 hot style. So if you're doing a state machine, right, in your state machine, your states are in 1 hot, which is really easy for a computer to automate for you. A ring counter will actually be the correct one to kind of walk you through your states. So that made kind of a nice, it was a very elegant thing. It's just a serial register where you just run the output and back into the input again. That's done. Right, so that's about as simple of a counter as you're ever going to build. And then we said, well, what if I want a few more states? Because that was very inefficient for registers. And we said, well, we could take that same serial register, put an inverter, and feed it back around. And that's sometimes called a switch ringtail or a Johnson counter. And the bits flipped as they came around. So it basically lets us have twice as many states for the same register, but similar types of properties. So it's also nice for doing state diagram stuff. We added 1 more counter type, which we called the non, 2 to the n or non-binary count. Right? In truth, what they are binary counters, where the maximum value is in a power of 2 to the n. So if you had like 10 bits, it would normally count from 0 to 1023. But what if you wanted to exactly count 1,000 things, 0 to 999? You don't want to count 0 to 1023. Well, what I would do is I would build a regular binary counter that counted to 1023, and then when I hit 999, I'd flip it over. And you could either do that by a reset, that's kind of the easy way of thinking about it, right? Or I could put a special case in there that, when I hit 999, it just transitions it to 0. All right, so that's easy to do with an if statement, right? Just your state area, you say if 999, next state is 0, else anybody else add 1. And that makes a very easy way to build those kind of not 2 to the n, which we just mean what the end state is. Otherwise, it's exactly binary. But there's a lot of times we need precision counting. That's basically all of Chapter 6. Chapter 8, we introduced the ASMD. So how do you just build something bigger? And we said register transfer level is the way to go. That lets us scale really nicely. And we just draw the state diagrams. We just turn them into the blocks. The square block is a state, a diamond is a decision, and the rounded corners means something that you do as part of a state, but after a decision has been made. And we could very easily turn this in. This is kind of simple statements. Here's my starting thing, right? Do these things, check this thing, do this thing as a result of it. And then we could repeat that pattern to describe any chunk of it. We just built up our whole area. So it was very easy from that building block set to pretty much build any type of a system we wanted. And it was also very easy from that set to turn into Verilog. All right, so that made a very nice, easy to scale, build whatever you wanted. We said that's kind of our capstone idea. right? If you have to build anything of appreciable size, ASMD is the way to go. Okay? And then we had this one last bit on here where we said, how do we do error correcting codes? That's it. Second half of the course. So I said 15 minutes. I did, that was like 12 minutes. you got like, 3 to 4 minutes. If there's a particular question, I'm happy to go into one of them in detail. But that's kind of my high level sketch of the second half. All right. So key things you might want to remember from the first half, right? Anything I didn't ask you design sequence-wise to do, because realize some of these things, like in Chapter 5, I could tell you to design something, you walk through the states, and you'll get what the combinational logic should be, right? I could tell you, hey, look, show me how to do, and I could pick any of our design techniques. Right? I could pick mux, I could pick decoder style, I could pick whatever, right? I can tell you, please implement that using it. So think about some of those design ones. Obviously, with the parity check stuff, it works nicely with ASCII and some of the other codes that came in. So that would be reasonable stuff to keep in your memories for it. So I would say that would be another one to definitely keep on the forefront of your thought process. And obviously, any of the designs we did here. Anything is fair game, but I've only got so much time. So you can try to reverse engineer. If I'm trying to figure stuff out, how can I maximize this considering what I've already asked you on the test? Because you've already had one midterm. I probably don't want to repeat too much stuff. I might randomly pick one of them just to make sure you don't completely eject your knowledge from those parts. But I'll probably emphasize stuff I didn't check. So it'll give you some thought about them. Any other questions? Awesome. So next time we'll move on to how we kind of build some of these FPGAs and the rest of it. I will see you all then. Let me see.
I actually do kind of have a question.
Sure. What's up?
How do you build edge triggering physically?
So there's a couple ways you could do it. The easiest way to think about it, it's not completely robust, but it's the easy way to think, is imagine that I had a edge, but a gated latch. Right? So a gated latch has a single gate, let's say a D and a Q. Does it make sense then how I could get a gated latch? Or should I cover that?
I forget the exact. It's like an or and a and crossed, right?
So we do
Yeah.
a NOR, another NOR, set, reset. Okay, that is a non-edge triggered.
Yeah.
Right? Whichever one of these is high triggers. So imagine I step this back a step, and I put an AND gate here. I put an AND gate here. I hook this to a clock. If clock is 1, S will pass through.
Yeah, then the whole thing can run.
And if clock is 1, R can go through. Otherwise, it's a 0 and it holds. Right? So that's, and then all I have to do is take the set, and I put an inverter, I'll get the reset, and now this is D.
Yep.
Right? And that is literally the interior. Right? So I can build this. We good?
Yeah.
Okay. This one only works when clock is high, not when clock is low. Right? If I were to take this and interior-wise put an inverter after the clock, it would only go when clock was low.
Yeah.
Okay. we do that this way.
Mhm.
Right? This one will only go when it's high. This one will only go when it's low. Right?
Okay.
I'm going to call this D0, the first one. I'm going to call this D1, the next D down the line, and then we'll get our final Q. Fair?
Mhm.
Okay. We're going to do a little time chart here. D0, D1, Q, and here's my clock. Okay. And let's say D is just kind of all over the place. Actually, I'll pick all kinds of weird different patterns. But they have to be zeros and ones, obviously.
Mhm.
Fair for a weird enough pattern. Okay. Now, on the first, right here, the clock is low. So this one's not reading anything.
Yep.
Right? So nothing's going through. So we really, honestly, we don't know what's going on here or here at the moment while this is happening. Right? Unknowns. The second I get to this clock, this one goes up, and whatever is happening here is going to get copied to the output. Right? As long as it's a 1.